So for the second talk this afternoon, we're pleased to have Eric Friedlander from University of Southern California, who will talk on intersections on singular varieties.
Thank you. I want to thank the organizers for inviting me. It's a real both honor and privilege, and an opportunity to give tribute to my friend and former collaborator, and who knows, maybe future collaborator, Blaine. As you all know, he's a wonderful person as well as a wonderful mathematician. Blaine and I did some work on algebraic cycles, and I think neither one of us has thought about it for a while, and partly inspired by this conference, I went back to look at what we were doing and trying to remember some of what we were doing. And I'm going to talk, this is a little risky talk. I'm going to talk about work that's most definitely in progress. If I get that far, I'll tell you how much of this conjecture I'm going to present that we can prove. Maybe we can prove everything, but that's was a subject of email last night, for example. So a little uneasy. I don't think I've ever given a talk about mathematics that's not at least in some form done, but here it comes. So I first want to give you the plan of the talk. So I'm going to begin by some recollections of complex algebraic geometry. So there are two philosophies in doing this, maybe wasting time doing this. Either you've seen it before and it's you'll just tune out. That's what happens when you take calculus kids and they've already seen it in high school and they just tune out. Or you haven't seen it, you couldn't possibly learn algebraic geometry in 3 minutes, but I'm going to do this anyway. And then I want to talk about intersection theory on smooth varieties, complex, projective. This is the subject we know. And in fact, I know very, very little about singular varieties, so this is daring for another reason. I'll mention just briefly something about singular varieties. Let's see. Then on my list is this conjectural intersection theory. And to give you a hint, this is an intersection theory that is, in some sense, a combination of work of Goretzky-McPherson and intersection homology, and work of Blaine and myself. And then, time permitting, I'll talk about partial results and possibly a few applications. So let's begin with our few comments about complex algebraic geometry. So we all know projective space, and all our varieties will be projective. So this will be, so it's just equivalence classes of n+1 tuples. But we don't view this as an analytic variety. We view as an algebraic variety. So in particular, one of the things that means is an algebraic variety, we keep in mind, we'll sometimes use the analytic topology, but mostly we'll keep in mind the Zariski topology. So I just want to emphasize what we're doing is algebraic geometry. And there's a sheaf of regular algebraic functions on this variety. And then we're going to be considering varieties that typically may have singularities inside some projective space. So we'll take X to be dimension D, and why not take it to be connected? And this is an algebraic subvariety. So by algebraic subvariety, we mean, this is my brief introduction to algebraic geometry, we mean the zero locus of finitely many, or of some, can choose to be finitely many, some homogeneous polynomials. In our variables z0 to zn, if you want. Those weren't variables, those were the names of a point, but in variables x0 up to xn. And then there are several very intrinsic algebraic pieces of data that we, in algebraic geometry, associated to an algebraic variety. One of them involves algebraic vector bundles, which are hidden in what I'm about to say. And the other involves algebraic cycles. So let me mention what an algebraic cycle is. An algebraic R cycle, it's called Z, on X, which is inside Pn. This is just a formal integer combination, finite sum, Ni and Z, where each yi is a subvariety inside X. That just means it's defined by even more homogeneous polynomial equations. And each yi is irreducible. So it's not a union of two such. So these are closed in X inside Pn, and we look at formal sums. So this is part of the algebraic geometry of X, which sits inside projective space. Fine. Then what we can do is we can put all these guys together. I'll use Z for another. I should use a different letter, but I won't. ZR of X, this is the group. Obviously, we can add two such guys. The group of R cycles on X. So this is an awfully big group. But we can look at that. It's a billion. Sum is there. And in some sense, in one of the ways to study an algebraic variety, one of the ways to get invariance, or just to think intrinsically because we want to know something about the algebraic variety, is to say something about the algebraic cycles. So these are completely algebraic in nature, but you can put an analytic topology. So this is I'll just say analytic space. It's actually infinite dimensional, but there is an analytic topology on this inherited from Chow varieties. And Chow varieties are somehow moduli spaces. If we fix an R, dimension of our cycle, then we can think of the Chow variety of R cycles of some degree. The degree is measured with respect to the embedding inside projective space on X. This is itself is a projective algebraic variety. And I think these are now back in vogue thanks to Blaine. Grothendieck pretty much eclipsed Chow varieties by looking at Hilbert schemes, looking at sort of infinitesimal nature. In any event, he looked at a more functorial version of Chow varieties called Hilbert schemes, but Blaine's work brought these Chow varieties back to the fore. Because they're algebraic varieties, we can talk about their analytic topology, and this inherits that. And just as an example, a non-trivial example, when R is 0. When R is 0, we're looking at irreducible varieties, subvarieties of dimension 0 or just points. And this is Z0 of X. You can think of as the free abelian group on X, showing you how big these cycle groups are. And it's topologized how? Well, in the case of R equals 0, this is topologized using finite dimensional pieces, which are just d-fold symmetric products of X. This would be 0 cycles on X of degree d. So you can put this is an algebraic variety, this is an algebraic variety, but it does inherit the analytic topology, if you will. And much of the theory that's been developed involving this, following work of Blaine, I call semi-topological theories or semi-topological algebraic geometry. We take a intrinsically algebraic geometry notion, but then we often look at it with the analytic topology. And in fact, I'd like to just put on my last part of summary, I think. Not actually looking at this, but it's very nice to have it in my hand. Some of you have heard of, and even some of you know better than I, what Lawson homology is, but we can define it right now. What one does is look at this space of R cycles as a group, but we put the analytic topology on, and then we take homotopy groups. And this would be LRH 2R plus I is the indexing of X. So it's a bi-graded homology theory, and turns out to be quite interesting. So I won't be talking about this per se. That's even further work in progress to do the pairings on higher homotopy groups. I'm going to suppress, in some sense, the topology. And for those of you who are familiar with this, I'm only going to be looking at pi naught. So rather than talk more about the topology, I want to talk about the most common equivalence relation that one puts on algebraic cycles. This is called rational equivalence. R cycles modulo rational equivalence. This is termed the Chow group of R cycles. And this, too, can be very big. It's not just a small discrete group. It looks like, for an algebraic curve, it's an extension of a finitely generated abelian group by a torus. So it still has its own, even though we've put an equivalence relation on it, it's still large. what is this equivalence relation? We say two cycles, Z0 and Z1, are equivalent, rationally equivalent, if and only if on X cross P1, well, better not. If and only if there's another cycle, Z, on X cross P1, and it's the existence of this P1, it's in that sense this is rational. If there's a cycle X, Z on X cross P1, it's flat over P1, such that the fiber over 0 is X naught, is Z naught plus something, plus a W, and the fiber over Z1 over 1 of this, these two are R cycles. This is R plus 1 on a bigger dimensional variety. If you look at the fiber over 0 and 1, we get back R cycles. And the equivalence relation is that possibly after adding something, the same thing to each, they live in a P1 family. This is a quite different relation if we replace P1 by a curve or by some bigger parameter space. It's not different if we replace P1 by Pn. So it's these Chow groups that one classically works with when you work with algebraic cycles. So now let me tell you a little bit about intersection theory for smooth varieties. So here is a theorem. I'm not sure if it's due to Chow, and it certainly it involved people. It involved work after Chow, but let's say it's due to Chow. If X is smooth, has no singularities, which, by the way, you can think of analytically. Say this variety, which is defined by algebraic equations, when is it smooth? It's smooth if and only if it has, at around every point, it has an analytic neighborhood that looks like open inside real 2D space. X is smooth. If X is smooth, then there exists a natural intersection pairing from the Chow group of R cycles on X across the Chow group of S cycles on X intersection to the Chow group of R plus S minus D. D is the ambient dimension of X. So it's a natural intersection pairing with lots of good properties. So I won't give the properties, but one of them is you could say it covers intersection of singular homology on manifolds. We don't actually need X compact, but the fact that I assumed X was projective gets me out of some awkwardness here. Covers intersection on singular homology and behaves well with respect to specialization. That's a very important property. Maybe I won't explain. So I'm not going to prove Chow's theorem, but in fact, I'm going to do the most simple toy example, which will have the proof in it. So let's take projective 2 space, and let's take a point in projective 2 space and blow up the point. So this will sit inside P3. And we can think of this as there's projected 2 space, and here's the point. And what we're doing is removing the point and putting in a P1. And my picture of the P1 will be like that. So this is our X. So all of this is X. And now let's take our cycle. Let's take the cycle E, which is E for exceptional locus. Which is this blown up P1. And now Chow tells us that if this is a dimension 1 cycle on a twofold, so we should have a pairing from 1 cycles cross 1 cycles to 0 cycles. In this case, the Chow group of 0 cycles, A0 of our X is just Z. So I should be able to give for any 2 curves, I should be able to intersect them and get a number. In particular, what is E dot E? Well,
so the blow-up of P2 at a point doesn't actually embed in P3.
Oh, sorry, it's not.
You could put it in P1 times P2.
Yeah, let's do that. Let me not worry where it lives. It lives in a big PN. You're absolutely right. So so we need to intersect these 2. Now, how do we do that? So obviously you can't simply, if you take their intersection is E. It's a curve. It's not. So the idea of Chow is to move. And this is Chow's moving lemma. Is you move one of the cycles, in fact, they're the same, but you move one of these 2 E's until it intersects properly the other E. And when you do this, the answer actually is -1. So even when we start out with 2 effective, namely without negative coefficient cycles, when we move, we're going to have, you necessarily will introduce minus signs. So, and what Chow's moving in this case, and this turns out to be a simple moving, is we want to move one of the E's to meet the other properly. Maybe I will put 4 here. So we want to. So what does Chow tell us to do? Well, he takes. Here's the E, and we write it as follows. We take P4 and we consider various projections down to P2. This is a variable projection down to P2. And associated to the projection, we have a mapping cone. So we have the mapping cone. I'll just say, maybe write it out, mapping cone with respect to pi of E. So what we do is we project E down, and then we look at the pre-image, and then we intersect it with X, and that's the mapping cone. So we have this mapping cone, and what we do is we look at E minus the mapping cone, and then we add back the mapping cone. And you have to agree that that really looks like it helps us a lot. So the idea is we intersect that with the other copy of E. Well, it turns out this intersects E well. In fact, and now this we move. So we couldn't have made any progress if we just added and subtracted the same thing. But the point is, we can act by PGL2 downstairs on the image, and then look at the pre-image and cut, and that'll be equivalent in Chow's group to the original. So we move this to meet properly. So this is the general outline of how Chow showed that there is an intersection product. Now, Blaine introduced a new way of moving in projective space. So in some projective space. So in fact, with this, I'll make a statement that applies to any possibly singular algebraic variety X that's a consequence of Blaine's result. It's a theorem of Blaine's. But this Blaine's moving had much more flexibility, in the sense that here we were acting by PGL2. That's not a very large group, but Blaine was able to act on cycles with very large dimensional space of actions, actually hypersurfaces of a given, depending on where we are in PN. But you look at, so you have these very big dimensional spaces. And what this enabled Blaine to do is, well, we'll see in a moment, it enables you to move families of cycles. So what's called the Lawson suspension theorem, maybe I'll highlight it, putting it on a higher line. Blaine showed that if you look at ZR of X as an analytic topological group, and if you can compare that with ZR plus 1 of, I guess Blaine calls this the algebraic suspension of X. This is, you put X in some Pn, and then you take a Pn plus 1, and you take a point infinity that's not in this Pn, and you look at all lines, the union of all lines from X to that point in infinity. That's the suspension, sort of like a topological suspension. And you can always take any cycle and just suspend it. So you have an inclusion like that. And Blaine's theorem was that's tonight. Homotopy equivalence. Induces an isomorphism on homotopy groups. And then the final part of my review is we which also lies behind what I'm about to say for singular varieties, is a theorem that Blaine and I proved. So in some sense, it's an extension of this theorem of Chow. So again, if X is smooth, which is essential, then there exists a pairing, continuous pairing, inducing the usual product on Chow groups. So I don't know if Blaine got any skepticism about this theorem, but I certainly did, because what this says, for example, in our special example of Z1 to Z0, is that in particular, there's this pairing, and it tells you what to do with E, comma E. And certainly, it seems counterintuitive that you could adjust things so that everything intersects everything else, because somehow you're going to get into self-intersections. And what's slightly hidden in this is this continuous pairing. The pairing itself is only unique up to homotopy, and there is some adjustment of homotopy that enables one to do this. Okay, this all fails for singular varieties. And I thought maybe I would motivate why look at singular varieties. But in the last talk, we saw one example of, or heard about one example of singular varieties. So we heard about Q-Fano. A favorite singular variety of mine is you look at the default symmetric product of some projective space. Say D and N bigger than 1. So it's a quite simple variety, but we know very little about it. Let's see. In representation theory, you see Schubert varieties that arise. So even if you start out with some focus on smooth varieties, and that was the message of the last talk also, singular varieties arise. So let me give you an example to show you what sort of thing can go wrong. And again, it's just going to be a picture. This example is due to Zobel. And it's, I guess, well known. It's in Bill Fulton's book. So let's look at P1 cross P1. That's certainly a smooth variety. It's mentioned too. And obviously, it's pictured like that. Well, here's a P1, here's a P1. And let's look at the cone on this. I'm already regretting my drawing. So I'm quite interested in this face of the cone, but then so our X is the cone on P1 cross P1. Okay? And let's take one of our cycles, Z. It's a 2 cycle. It's that face of the cone. And then let's look at a few other 1 cycles, and we want to intersect the 1 cycle with a 2 cycle. That's the intersection theory we're interested in. well, let's call this curve L1, and this curve L2, and maybe this curve L infinity. So we have trouble intersecting L infinity with Z, but it's not too much trouble because all of these edges of this P1 cross P1 are rationally equivalent to each other. L infinity is equivalent to L1, is equivalent to L2. I mean, we can just fold it down and then fold it back up. So that's not so bad. But then what is really disturbing is that L2 has intersection with Z, giving us the answer 1, and L1 has intersection with Z, giving us the answer 0. There's something strange that's happening. It's equal to 0 in L2. So this leads us to Goretzky-McPherson intersection theory. And I'm already way past my time budget. So I'll just say, following Goretzky-McPherson, I want to introduce the following definition. So given a stratification, and we're going to choose a stratification soon, of X, so to keep things straight, I'll go down. This is codimension. Given a stratification by closed subvarieties with certain properties, which we will ignore, we say that the R cycle Z on X has perversity P over line, which is a D plus 1 tuple of numbers. If you take the support of Z, well, it's actually you take each piece of Z. Maybe I should take the irreducible one so I won't get into trouble here. If you take the support of Z, so now we can just take the Z. If you intersect Z with Xi, Xi has codimension I in X. We want to talk about how well Z meets all of these strata. So if the dimension of this well, the best possible thing would be if Xi just met Z properly. So then it would have dimension R minus I. So if it's less than R minus I plus P of I. So that's where the perversity allows a bigger dimension than proper dimension for the intersection. And the condition on the perversity is, let's just call it P without the P of 1 is equal to 0, and P of I of P of I is less than or equal to P of I plus 1, which is less than or equal to Pi plus 1. And I'll want the top perversity. This is top perversity. T of I is I minus 1. Okay. So the idea is of Goretzky-McPherson is if we control how our cycles intersect strata, and especially if the strata have something to do with the singularities, then we should be able to intersect. Now what's going wrong here is that, notice if we want to move L1 into L2, we have to go through the singular stratum. Okay. So I have various remarks about when we can intersect, and I'll just say one, sort of just to get it out of the way. So I'd like to intersect a Z, which is an R cycle, with a W, which is an S cycle. Let's say R, S. Now, if one of these is a what's called complete intersection, if it's given, if it's produced from X by, let's say, R, X has dimension D. So this has codimension D minus R. If our cycle Z is just given by D minus R equations, it's called a complete intersection, then Z sitting inside X, I'm assuming it's irreducible, I guess. This is a very nice map. And Fulton McPherson tell us how to intersect. This, what one does is one sees that in this condition, we'll have a normal bundle to this embedding. And Bob McPherson introduced a beautiful construction of deformation to the normal cone, but in this case, normal bundle. So what we want to do is intersect W with Z, but it turns out with this deformation process, you can intersect W with the zero section of this bundle, and then you can do it. So that's one case in which one knows how to intersect. There have been some attempts to define an intersection product or to think about intersection products. And I just want to mention a student of Blaine's name, Paul Geyer, whose work may come in but later. And I'm not sure when, and a student of mine named Christopher Flannery, these both wrote their theses maybe roughly at the same time. They did quite different things, probably over 10 years ago. But there has been some work thinking about this. Maybe what I should do is tell you this conjecture before I tell you any partial results. So we certainly can prove this in many cases, and we may have a proof in general. So we take X, and we look at a resolution of singularities of X. This is smooth, still projective. And the subtlety is choosing the resolution of singularities well. And then we give X a stratification, depends on the resolution. This is one of the tricky things. It seems to be wrong that groups will get, these intersection homology groups are independent of the stratification, whereas Goretzky-McPherson can show that their groups are indeed independent of the stratification. Anyway, we pick a resolution of singularities with good properties. We give X a stratification so that Xi is approximately the set of X and X such that the pre-image, well, maybe I should say Xi minus 1. plus 1. It's the set of x and x such that the pre-image has dimension, what do I want? Less than or equal to I minus 1. Now, if anyone who's following this will say, well, these things, xi may not have codimension I. It may have, I have to do a little bit of re-indexing, but I won't worry about this. It'll have codimension I or greater. So associated to a resolution, we get a stratification, and that stratification is in the background. So Joe Ross, who's a postdoc at USC, and I have been considering how to intersect on singular varieties. And our conjecture, after some examples, is that you should have a pairing from R cycles of perversity P on X cross S cycles of perversity. Now, I want to make it the complementary perversity, so I'll write it suggestively, but this is not quite right. It's the complementary perversity on X to R plus S minus D cycles. Well, let's just say this. By the end of the lecture, I'll know how to catch the chalk. So notice we have no control on perversity in the target, unfortunately. So should there be time, which I doubt, I'll tell you all sorts of situations in which we know this to be true. I wanted to mention one general principle about how you would pair, take a cycle Z and a cycle W, and form their intersection. The idea is that the problem with the intersection is that the singular locus gets in the way. And we can't move, this picture is very good. We can't move sometimes, this picture doesn't show it, but sometimes we can't even move two cycles so they meet properly in order to take the intersection. And even if we could move two cycles so that they intersect properly, like in dimension 0 for these two, they may not be, the moves may not be equivalent. So one thing you can see is that if you look at, maybe I'll write it over here. Oh, T is this top perversity. So this is just saying it's the complementary perversity. So one principle is if ZW satisfy a property we call star, that is that the support of Z, that's the union of the supports of all the pieces, intersect the support of W, intersect the singular locus of X. If this has dimension less than R plus S minus D, then intersection can be defined naturally. Namely, we just restrict to the smooth locus of X, intersect, and close up. And what we want to do is make sure we don't miss any of the pieces that should be the answer. So this is almost self-evident. But the technique is to try and move one of these, either the R cycle or the S cycle, so that the pair of them satisfy star. Now that's pretty hard still because we're still confronted with intersecting with a singular locus. So rather than talk about special properties, I thought I'd go back and special cases of this. I thought I'd go back and say something that's really actually easy. You'll see there's no moving involved, but is reminiscent of another aspect of work of Blaine's, actually Blaine and myself. So, so this isn't actually what we want, and I'll mention why it's not what we want, but it actually sounds better than the conjecture. So here's what you could call a theorem. Even though I did, I wouldn't. For any stratification on X, not necessarily one coming from a good resolution of singularities, there is a natural pairing from, this is a different T. Well, it doesn't have an overline. Codimension T cocycles of perversity P. This is, or maybe, well, let's call it that, cross dimension S cycles of perversity Q to S minus T P bar plus Q bar of X. Well, we already know, I've mentioned, you probably have forgotten, but I've mentioned what I mean by cycles of a given perversity. That's how they meet the perversity controls, to what extent they do or don't meet the strata properly. Now, Blaine and I introduced something called morphic cohomology. And to do that, we introduced what we called algebraic cocycles. And what this gadget is a generalized algebraic cocycles, generalized in a very natural way. So I just want to tell you what these guys are, and then I'll stop. So where some, let's call it alpha in Z, T, P bar, X by definition is represented. So what is such a gadget? It's represented by a difference of such things, but by a rational map. Means not defined on a Zariski open set. From X into a Chow variety of 0 cycles on PT. That's the codimension. So Blaine and I's algebraic, for us, algebraic cocycles were represented by morphisms from X into cycles on projective space. This is only a rational map, but every rational map has a graph whose graph gamma A, that's inside X cross PT, has fiber dimension over xi inside xt, no greater than I minus 1. And indeed, it was thinking about how to think about things in terms of cycle, generalized cocycles, and cohomology that we first got involved with pairings on algebraic varieties. Thank you very much. Question?
So if instead of directly working with the singular varieties, you were to make a resolution of singularities, I guess you already have an intersection theory there. And how are they related?
Yeah, well, you get something different. But even more than that, if you want to keep perversities, what you can do is you go up. One of the problems of this is you want to intersect cycles on X. So you go up to X tilde, which is what we're doing, in fact, or we're doing partial resolutions. But you go up to X tilde, and then you sort of flatten out or adjust your cycles up there. But then you have no control when you push the cycles back down how badly they meet the singular locus. You just lost all of that. So the whole point of moving up to the resolution, X tilde, is that you can then adjust things to meet properly. But and the adjustment's basically happening above the singular locus. But when you do this, you're most definitely changing the pre-image above the singular locus, and you lose all control of that. But in fact, the answer is different. You are not getting the good notion of intersection is not just intersect upstairs and push down. Yeah. Blaine.
So you sort of indicated this, something about this in the beginning, but what's the relationship to, is there some natural transformation to
Yes.
intersection homology?
Yes, assuming we have the pairing, definitely. I mean, this will just map, yes.
And over here with this theorem, there's a...
Yeah, so I guess there would be a natural transformation with the, this is what I would call slant product, or basically a cap product. Yeah. So
you indicated that somehow this stratification was not independent of...
Yeah. The definition of the groups or the perversities depend on the stratification. And we choose a stratification depending on a well-chosen resolution of singularities. But even if we have the theorem, we don't see how, when you move from one resolution of singularities to another, how the answer changes.
But on the other hand, the interesting McPherson theory is independent.
Yes.
I see. So
that's a real theorem.
That lies in the kernel of this map.
Or maybe there is no kernel. Paul.
Yeah, in the work of Geyer, as you mentioned, he defined the so-called intersection Lawson homology. Although I have never seen the morphic counterpart of that. So can you do that using this pairing and then have sort of a duality in that context?
So, first of all, duality, the usual sense of duality is just wrong even in the smooth case. In the sense, you don't expect let's say, codimension R cycles and dimension R cycles, the Chow group of codimension R cycles and the Chow group of, that's just wrong. You might have a pairing. Now, what I was sure you were going to ask is, I have this, and in fact, I should have put it there, modulo some equivalence relation, which I didn't specify, but again, it's rational equivalence respecting perversities. Now, what's very natural to say is, how about taking not taking equivalence classes, but taking homotypic groups? That's what I thought. And then what is even more natural is to take Geyer's form of homotypic groups, which for 0 cycles, he shows how you recover intersection homology. So Geyer's homotypic groups are stratified. Well, that's more work in progress, because it's one thing just to pair on equivalence classes. It's another to pair on, let's say, an I sphere of these and a J sphere of these. Then you need much more dimension of moves. And that's the beauty. We don't have enough moves at the moment at all. And the beauty of Blaine's theorem, maybe it's no longer here, is Blaine gave us big families of moving so that we could move an I sphere with a J sphere.
Yeah, but your work with Blaine also, you move even bigger families.
Oh, yes. We move, but we don't, at the moment, we don't have such an analog here.
Any further questions?
you can put the topology on the right-hand side.
So that's what I was saying, that it's much easier to move, just to talk about pairings of equivalence classes than pairings of continuous pairings of groups, or even up to some homotopy. So at the moment, I would make no such claim, except in special cases. On the other hand, implicitly, I did make that claim for co-cycles and cycles. But yeah, but this is okay. But that, I'm not claiming this even as it's stated. I'm saying as it's conjecture. Yeah.
You said in music conjecture some examples?
Yeah. Well, we know it when p bar is 0. We know it in when you're intersecting with divisors, which means Weil divisors. If they're Cardet divisors, then Goretzky-McPherson tells you how to do it. We know it for three-folds, most four-folds. I mean, yeah. So we know it in a lot of examples.
More questions?